Hi, everyone. And so, hi, thanks for the nice introduction and thanks for having me. I hope you all can see my slides here. So my title for today is New Results on Disconnectivity of the Parameter Region of Multistationarity. You might have heard me last year talking about connectivity of the parameter region of multistationarity. Today, in the first part of the talk, I'm going to recall these results, and in the second part, we will look at some new results. And at the very end, I will also discuss a reaction network where the parameter region of multistationarity is disconnected. So basically, I'm going to look at the same objects that Carsten was looking at it. But unfortunately, my notation is a little bit different. So let me just fix the notation. So I will write capital Xi for the species, and I will have some reactions. And here is a running example that we will revisit in the first part of the talk, just to see that what we are doing is nothing magical. So for the stoichiometric matrix, I will write capital N. Remember, this is the matrix where the columns have the information about the net production of the reactions. For the reactant matrix, I will write capital A. So here, the columns are the reactant complexes. And I think I have forgot to mention that I also like to work under the assumption of mass action kinetics. So our reaction rate function is going to look like something like this, which is kappa is the vector of reaction rate constants. And we just take the pointwise product with this monomial vector x to the a, where a is the reactant matrix. So far, so good. With all these objects, we can write down the ODE system that we are interested in. And for the steady state variety, I'm going to write V kappa. So this is all the point x's such that the ODE is a steady state. For the stoichiometric compatibility classes, I'm going to write PC. At this point, we have the same notation with Carsten, which is great. And but unfortunately, I will write a W for the matrix containing the conservation laws. So here, the rows of the matrix W corresponds to conservation laws. So far, so good. So these are just the basic notions that I will use. And if you look at the running example again, then we have two steady state equations and one conservation law. And since we only have two species, just a second. Yeah, since we only have two species, we can make a nice drawing if we can. Yeah. So here, the purple curve is the steady state variety for different choices of kappas, and the green lines are the stoichiometric compatibility classes. And we can see that for some choices of parameters, we have only one intersection point, but for other choices of parameter pairs, we might have more than one. So in that case, we have 1, 2, and 3 intersection points. And whenever it happens that we have at least 2 intersection points between the steady state variety and the stoichiometric compatibility class, I will say that this parameter pair enables multistationarity. And I will write omega for the set of all parameter pairs kappa C, such that we have a multistationarity, meaning that the intersection of the steady state variety with the stoichiometric compatibility class contains at least 2 points. And our goal today is to look at the shape of this parameter region of multistationarity, to look at the shape of omega. And the basic question that we ask here, is this set a path-connected set or not? Okay, so how can we say something about the shape of the parameter region of multistationarity? Most of our argument relies on this theorem, what I call the key theorem. But before I say this theorem, let me just introduce a matrix, M kappa of X. So this is just the matrix. This is the Jacobi matrix of the following function. So first I take the steady state equations, and then I replace some of the rows by the rows of the matrix W. So W is the matrix containing the conservation laws. And in that way, I get a function, and I take the Jacobian of this. And this is the matrix M kappa of X. Once I have this matrix, then I can say the key theorem. Here we have two assumptions assumptions on the network. First, the network should be dissipative without boundary equilibria. And whenever it halts, then we can look at the sign of the determinant of this matrix that we just introduced before. And if this sign is negative for some x in this intersection, then the pair kappa c lies in the parameter region of multistationarity. If the sign of this determinant is positive for all the x's in the intersection, then the pair kappa c does not enable multistationarity. So in that way, we have a nice way to decide whether points lie in omega or not. If you go back to the running example, then the determinant of this matrix looks something like this. And if I pick a point on the steady state variety, let's say I pick the point here to be 0.25 and 2.75, then I can evaluate the determinant. I get a negative number. So the key theorem tells us that the pair kappa and c lies in the parameter region of multistationarity. And this is exactly what we see here in the picture. We have multiple steady states. We have 1, 2, and 3 steady states. So far, so good. But here, the important thing is that we have to evaluate this determinant at points such that x is in the steady state variety with parameter kappa. And for that, it's very useful to have some kind of parameterization of the steady state variety. For example, you can use monomial parameterization if you like monomial parameterizations. But today, I will use a different type of parameterizations, namely so-called convex parameters. And for that, first we have to look at the flux cone, which is just the kernel of the stoichiometric matrix M intersected with the non-negative order of R to the R. And the reason why this cone is so interested, if we know that x is in the steady state variety B kappa, then by definition, the reaction rate function lies in the kernel of M, and it has non-negative entries. So this reaction rate function is going to be contained in the flux cone. And the flux cone is a very nice polyhedral, convex polyhedral cone. So you just can compute the extreme vectors of this cone, and you can write every element in the cone as a non-negative linear combination of the extreme vectors. So for every reaction rate vector v kappa of x, you can find a lambda such that E times lambda equal to this v kappa of x, if x is in the steady state variety with parameter kappa. And using this observation, one can write down a nice parameterization. So here I want to parameterize the set of x and kappas such that x is contained in the steady state variety with parameter kappa. And in that way, I can just write down this parameterization here. And this function is going to be a surjective function if E does not have any zero row. If E has a zero row, then there are no positive steady states. So this case is a sort of uninteresting for us. So we're going to assume all the time that E does not have any zero row. In that way, we get a nice parameterization. And the other nice thing is that if we look at the Jacobi matrix of this function evaluated at this point, then it's going to look like this product of matrices here. So remember, in the key theorem, we worked with the Jacobi matrix. So here we do the same. We replace exactly the same rows as before by the rows of W. And in that way, we get this matrix M tilde lambda and H. And then if I take the determinant of this matrix, this is going to be a polynomial and the lambdas and the H's. And that is what I'm going to call today the critical polynomial. And basically, that is the reason why I personally find convex parameterizations better than monomial parameterizations, because if you look at the determinant of this matrix, you always will have a polynomial instead of having some rational functions of the unknowns. Okay, so once we have this critical polynomial, then we finally can say something about connectivity of the parameter region of multistationarity. So we look at this determinant. We have exactly the same assumptions that we had before, namely dissipativity and no boundary equilibria. And if I know that the closure of the preimage of the negative real line under Q equals to the preimage of the non-positive real line, then the number of path-connected components of the parameter region of multistationarity is bounded above by the number of connected components of the preimage of the negative real line under Q. So meaning, if I can show that this number here on the right-hand side is 1, and I know that omega is non-empty, then we will know that the parameter region of multistationarity is connected. And if you look at the running example, then the critical polynomial is this cute small polynomial here. And in fact, you can ask, for example, Maple, and Maple will tell you that this semi-algebraic set here, so the preimage of the negative real line under Q is a path-connected set. And if you want, you can check also this closure property by hand. So putting everything together, one concludes that the parameter region of multistationarity for the small running example is connected. But believe me, for larger reaction networks, this critical polynomial can be crazy large. So, and Maple will not tell you whether this set is connected or not. So for that, we have to do something else. And here is a condition, a sufficient condition, that works for surprisingly many reaction networks. So whenever I have a polynomial whose domain is restricted to the positive ortho, then I'm looking at the set of exponent vectors, and I want to split up the set of exponent vectors into two subsets. Namely, I want to look at the set of negative exponent vectors, and by those I mean exponent vectors such that the corresponding coefficient is negative. And the set of positive exponent vectors is defined the same way. That is all the exponent vectors such that the corresponding coefficient is positive. And here in the drawing, the blue dots corresponds to negative exponent vectors, and the red dots corresponds to positive exponent vectors. And in the theorem, what we want to have a hyperplane that separates these positive and negative exponent vectors. So in the drawing, a hyperplane is just a line. And we want that on one side of the hyperplane, I have all the negative exponent vectors, and on the other side, I have all the positive exponent vectors. And additionally, I also want that there exists at least one point, one negative exponent vector, which is not on this hyperplane. And whenever this is satisfied, then the preimage of the negative line is path connected, and this closure property is also satisfied. So these are exactly the two things that we need for the criterion of connectivity of the parameter region of multistationarity. And to check whether such a separating hyperplane exists or not, you just have to solve a linear program. So it works quite well for networks of moderate size. So here are some networks where we could apply this method. So first, let's look at this two-side phosphorylation system. This is exactly the same network that Carsten was talking about before. Here we have a substrate, and it gets phosphorylated and dephosphorylated. It turns out that these type of networks are dissipative without boundary equilibria, so we can compute the critical polynomial, and one can also check that the support of the critical polynomial has a separating hyperplane. So the conclusion is that the parameter region of multistationarity for the two-side network is connected. You can modify these phosphorylation cycles. For example, you can assume that the phosphatase F here, they are different in each phosphorylation step. In that way, you can get another reaction network, and the same goes true also for these type of networks. So what you can do, to check how good is your method, you can just increase the number of binding sites in the phosphorylation system. And for the four-side phosphorylation system, everything works fine. But if we go to the three-side phosphorylation system, unfortunately, we were not able to compute the critical polynomial. And that was the point when we had to come up with something else. So let's have a look at these two four-side phosphorylation networks. In both networks, we have motifs like this. So here are the elementary reactions. And the idea was, what about if we just remove this backwards reaction here? Could we say something about the original reaction network? So here is a quite technical proposition. So here I assume that there are species in the network, x1 up to xk, that are participating in exactly three reactions of this form. So remember, these are exactly the reactions that we had before here. And I want to look at the critical polynomial of the reduced network. This is the network when I just remove this reaction that go backwards. And the statement is that if the reduced critical polynomial satisfies this closure property, then the number of path-connected components of the preimage of the negative real line under the reduced critical polynomial, this gives me an upper bound for the number of path-connected components of the parameter region of multistationarity of the original network. So the moral is, let's remove these reactions, compute the critical polynomial, and say something about the original network. And in fact, by removing these reactions, we were able to compute the critical polynomial for the four-side phosphorylation system. The good news is, if you have different phosphatases, then the support of the critical polynomial has a strict separating hyperplane, so everything is nice, and you can conclude that the parameter region of multistationarity is connected. Bad news is, you don't have a strict separating hyperplane for the four-side phosphorylation system with the same phosphatases. So here we have to do something more, but for that we have to go back to the world of polynomials and polytopes. So let's consider a polynomial f, and I'm going to write n of f for the Newton polytope of f, which is just the convex hull of the set of the exponent vectors of f. And the Newton polytope is a nice polytope. It's going to have a finite number of faces, and I'm going to denote the face corresponding to with outer normal vector v by n f of v. So here is just a picture of a three-dimensional Newton polytope corresponding to this polynomial here. And here, this blue square would be one of the faces of the Newton polytope. But also, we have zero-dimensional faces, for example, these edges here. So there are a lot of results how the polynomial depends on the Newton polytope. And here is a very useful thing that was at least useful for us. And the statement is that if I know that exists a face of the Newton polytope such that all the negative exponent vectors are contained in that face, then the number of path-connected components of the preimage of the negative real line under F is the same as the number of path-connected components of this restricted of the preimage of the negative real line under this restricted function. And with by the symbol, I just mean the polynomial where I collect all the monomials such that the exponent vectors are contained in the face F. So if we are looking at this polynomial in 4 variables, we can see that these 8 terms here does not depend on W, and the terms which are depending on W, they have all positive coefficients. So the set of negative exponent vectors will be contained in that face with outer normal vector 0, 0, -1. And the theorem just tells us, instead of looking at this little bit larger polynomial, I can look at a little bit smaller one. And the hope is, if I do this reduction, this polynomial is small enough that I can say something about this polynomial here. If this is not small enough, then you can do another type of reduction. So here I will have a little bit more assumptions. So here I want to assume that I have 2 faces of the Newton polytope, which are parallel to each other. So if we look at this picture here, we can pick this bottom face and this top face of the Newton polytope. And I want that all the exponent vectors are contained in these 2 parallel faces. These 2 faces are completely fine for the theorem. And I want to assume that the preimage of the negative real line under this restricted polynomials are both path connected. If you look at the picture, the top face satisfies this property because here we have a strict separating hyperplane, and so does the face at the bottom. The second assumption I need that the intersection of these 2 preimages is non-empty. In practice, it could be hard to verify this, but if you are lucky and if you have an edge between the 2 parallel faces such that the vertices of this edge corresponds to negative exponent vectors, then this intersection will be non-empty. So it's sort of easy to check. And if all these assumptions are satisfied, then the preimage of the negative real line under F is connected. So using this theorem, you can sort of split up your problem into 2 smaller polynomials. If you go back to this polynomial in 4 variables, then we can sort of see in this picture what the algorithm does. So in the first step, we restrict the polynomial to a face that contains all the negative exponent vectors. And then I'm starting to look for parallel faces. And then I find two parallel faces. And if I'm lucky, these two parallel faces are easy enough that I can conclude that the parameter, then the preimage of the negative real line under these polynomials are connected. So let's go back to the four-side phosphorylation system. Remember, that was the one network where we didn't have any strict separating hyperplane. And it turns out we can play this game here. So first, so Q is the critical polynomial corresponding to the four-side phosphorylation system. First, we reduce to a face of the Newton polytope that contains all the negative exponent vectors. Then we look at two parallel faces. One of the faces has the property that it has a strict separating hyperplane. For the other face, I have to split up again my problem to two parallel faces, but both of these guys have a strict separating hyperplane. And here I also have a negative edge between the two parallel faces. So putting all the arguments together, one can conclude that the parameter region of multistationarity for the four-side phosphorylation is connected. And here's the funny thing. You can do the same game for number of binding signs equal 5, 6, and 7, and you get exactly the same pictures. So, now the conjecture is, does it happen for all n larger than 4? And this is something we do not know, but it would be pretty nice to investigate. So here is just another network where you can play this game, but let's just skip this example. And at the beginning, I promised you that I will talk about a reaction network where the parameter region of multistationarity is disconnected. So here it is. So here we have also a substrate that gets phosphorylated and dephosphorylated, and we only have one binding site, and we also have these 4 additional reactions. Using the trick with the critical polynomial of the reduced network, one can conclude that the number of path-connected components of the parameter region of multistationarity is at most 2. But the more interesting thing is that it is actually equals to 2. And how can we show that? Well, for that, we have to look at the key theorem again with a different type of parameterization. So here you can use this monomial parameterization, which is obtained by just solving the steady-state equations, like Carsten was telling us before. In that way, you get a nice parameterization of the steady-state variety. And using the key theorem that I showed you before, part B of this key theorem implies that the parameter pairs kappa C such that kappa 3 is equal to kappa 6, and they are never contained in the parameter region of multistationarity. So here in the picture, we fixed all but these 2 parameters, and we fixed kappa 3 to be 1. So here we have this nice hyperplane where kappa 3 is equal to kappa 6. And by part B of the key theorem, there are no points from omega on this hyperplane. And using part A of the key theorem, one can also show that we have points from omega from the parameter region of multistationarity on both sides of the hyperplane. So this region cannot be path connected, because whenever I have a point here and I want to find a path that goes to a point from the other side of the hyperplane, I have to cross this hyperplane. And that shows that it cannot be path connected, but earlier we saw that the number of path connected components is bounded above by 2, so it must be equal to 2. And that's everything that I wanted to tell you today, and thank you for your attention.